Hello folks, and welcome to our last video of part 1 for chapter 11 information. Part 2 is for our Tuesday lecture, so just keep that in mind. If you have any issues of figuring out when the parts are going to come out, make sure you go to the lecture and lab schedule on the home page. Now for this video, we're going to be focusing on resting membrane potential first, and then we're going to talk about changes in membrane potential. Because if we understand resting, then when we get to those changes, it'll make it a little bit easier for us to make sure we can understand new terminology and get the details down as we start adding in more layers of information. So first, we got to talk about what is membrane potential and also what does rest mean. So for a neuron cell, being at rest means that the actual neuron is not trying to move any type of communication. It's not communicating within the cell. That means it's not trying to move any messages through the cell body down the axon. It's not trying to receive messages at all. There's no communication happening. And then what is membrane potential? Membrane potential is basically saying that the inside and the outside of the cell have different charges. And if you have a difference in charge, you have an electrical potential. Now, for most neurons, okay, and mostly everything we're going to learn in our textbook, resting potential is going to be negative 70 millivolts. What does that mean? Well, first, let's go ahead and get oriented. We have our membrane here, we have outside the cell, and we have inside the cell. And inside the cell is going to have a voltage of negative 70 millivolts at rest. So anytime you're thinking of a neuron at rest when it's not communicating, you should always say the interior of the cell is going to be more negative than the exterior outside of the cell. Now the next question is, well, how? How do we get that negative 70 millivolts inside the cell? Well, that resting potential is going to be created by two things: the differences in ionic composition and the differences in plasma membrane permeability of those ions. So what has been our focus? Our ions of focus have been sodium and potassium. Now, when it talks about difference in ionic composition, remember we said that when you're talking about sodium, sodium is always going to have a higher concentration on the outside of the cell. Every time you see anything that's within these little brackets here, that means that you're talking about concentration, okay? You go ahead like that. And then we also said that the potassium is going to have a higher concentration inside the cell. And because of that, what do we also say about passive transport? Well, those leak channels are going to be moving potassium outside the cell because it goes from a high concentration to a low concentration. And it's also going to be moving sodium inside the cell because it goes from a high concentration on the outside to a lower concentration on the inside. And that is going to help us be able to get that membrane potential be more negative because, again, you have potassium leaving the actual cell interior. But there's also going to be differences in plasma membrane permeability. Remember, we're dealing with a semi-permeable membrane, but we have proteins like these leak channel proteins that are going to allow ions to move in and out. And because potassium is going to have a higher concentration on the inside of the cell, it's going to actually move out of the cell, which is going to contribute to removing positive charges from the inside of the cell and contribute to the negativity. But one thing we notice here in this image is that we have way more potassium leak channels than sodium leak channels. And we have to think about, why is that important? Well, number one, potassium is very important for other things besides just creating this membrane potential. It helps with pain signaling, helping you with how long you sleep, and also a little bit with movement. Okay, so that's going to be something that's important. So yes, we need to find a way to make sure that potassium can come out of the cell, and therefore you'll see that potassium has way more leak channel. Now again, sodium is important as well, and potassium is not the only thing that contributes to that negative 70 millivolts. There's other ions and proteins that are negatively charged inside the cell that do that as well. But for us, of course, we're focused on potassium and sodium. So to create this membrane potential of negative 70 millivolts, again, we need more leak channels for potassium, and we also need leak channels for sodium, and we need to make sure they're going with their concentration gradients and diffusing from high to low. Okay? But we also have to ask ourselves, well, how do we keep this stable? Because what if we have a situation where too much potassium is diffusing outside the cell? Maybe you're dealing with a lot of pain and you need a lot more potassium. How do we maintain the concentration of potassium inside the cell and the concentration of sodium outside the cell? Well, that's where our good old sodium potassium pump comes in. So of course, with the sodium potassium pump, we're going to have 3 sodiums that are pumped out into the extracellular fluid and 2 potassiums that are pumped in to the actual cell itself. So because of that, that's how we're able to stabilize and maintain the concentration gradients to keep the concentration of potassium high on the inside of the cell and keep the concentration of sodium high on the outside of the cell. And it's the sodium potassium pumps that helps maintain that concentration and keep things stabilized. And we just definitely don't want a situation where too much potassium is leaking out. Now the cell is even more negative, because if the cell gets too negative and it goes even below -70, like to say to -100 millivolts, for example, it will be harder for the neuron to communicate. And we'll see more details of that as we continue to go along with the lecture. Just to reiterate here, if the sodium potassium pump is stabilizing the concentrations of sodium and potassium by making sure sodium is going to have an increased concentration on the outside and potassium has an increased concentration on the inside of the cell, that also means that it's basically stabilizing that rate of diffusion of potassium going out and sodium going in, which is very important. So just think, sodium potassium pump is all about maintaining the concentration gradients and stabilization, but to create the membrane potential itself, we need the differences in sodium and potassium, and also we need the permeability differences as well, meaning more leak channel proteins for potassium than sodium. So we focus on resting membrane potential. We know that at rest that we have a cell interior of -70 millivolts. But of course, neurons cannot always be at rest. They need to communicate. They need to be able to receive signals and transmit signals, right? So when it does have a change in membrane potential, because it can't be at rest forever, two types of signals can happen. You're either going to have a graded potential or an action potential. And we're going to get into detail of those as we go along in the lecture. But before we can even understand graded potentials and action potentials, we have to really understand some new terminology. So we definitely have some new terms we have to get into. And the easiest way to understand these terms is to create a graph. So on the x-axis, you're going to have times and milliseconds. On the y-axis, you're going to have membrane potential in millivolts. And so we did talk about having our cell at rest at -70 millivolts. That's our cell at rest, okay? And we just talked about that. So there is a term that goes along with our cells being at rest, and that term is polarized. So when your neurons are at -70 millivolts, then it is at rest, and that's going to be considered polarized. Okay? That means the inside of the membrane is negative. We know it's going to be about -70 millivolts. Let me just write negative here. And that's a term we'll use. So instead of just being like, it's at rest, we can say, it's at -70 millivolts. Boom. And then the next thing we want to see is what happens when this overall membrane changes. It's no longer at rest and it gets more positive. So first, let's look at the y-axis itself. We see that we have the 0 here. And so the 0 is right in the middle here. Well, almost. And when you go above the 0, you're getting positive. When you go below the 0, you're getting negative, right? So that's what we know about our graph. I mean, another way to say it is, you could just write this out for yourself as well. Say we're getting negative here. So if you just had a line here and you had your 0 mark, and this was 0, then this will be +1, this will be -1. And so that's exactly what we're doing here. And having this overall graph is really helpful because these are the graphs you're going to see as you go along when you're learning as well. Okay, so if at any point you're at rest and the overall membrane gets more positive, then you're going to have a new term. Instead of just saying it gets more positive, you're going to say that the membrane is depolarized. And it's called depolarization, okay? And this means anytime as we go through, and this is a new terminology we're adding on, we're saying, hey, the membrane is going to change. It can't always be at rest. It can't always be polarized at -70 millivolts. It's going to change. And when it changes, there's multiple ways it can change. It can get more negative or it can get more positive. So if it gets more positive, we're talking about depolarization. As you can see, we're going from -70 all the way up to +30. And these are the numbers that you're going to see a lot of as well. Okay? That's what depolarization is about. And that means you're going to have a temporary decrease in membrane potential. So this is where some folks will be like, what do you mean decrease? Because remember, this is -70 going down to +30 or going up to +30. So what that means is you're going from a negative number to a positive number. That means you're going to be decreasing the membrane potential because you're not going to be -70 anymore. So just keep those in mind. Now, of course, you also can't be very positive for this extreme amount of time. That means you're not going to stay depolarized. So what do? You have to then become negative again. So the inside of the membrane becomes negative again. How does it become negative? Through a process of repolarization. So we're like, okay, well, it's polarized, that's negative. Well, how can we have something called repolarization? Remember, repolarization is not at rest. Repolarization happens after your membrane potential becomes positive. And of course, because we're talking about neurons, we want to make sure it gets back to rest at some point. So it will go back down to -70, and that's what the repolarization means. So easy way to remember this is depolarization means you can actually say decrease in the membrane potential. Repolarization means return to -70 millivolts. That's what that means. Or you can say return to resting potential. Either one you want to say, okay? Now, guess what, folks? When you're repolarizing, sometimes you go a little bit too far. And that means that you can have a situation where you're actually going to be more negative than when you're at rest or when you're polarized. And so if you just continue to go beyond the actual resting potential and become more negative, as we see here, there's a term for that as well. That's going to be hyperpolarization. So we're going to put two little negatives here, negative signs, because we're talking about it's going to become even more negative. Okay? That means you're going to have a temporary increase in membrane potential, because you're going from -70 to maybe like -90, for example. All right, folks? So just keep that in mind as well. So you can put like a little bit -90 just so you can keep your brain processing. And this is going to be called hyperpolarization. So you know hyper means that something's happening a lot too much. So we're thinking it's too much negativity now. We've been beyond the actual resting membrane potential. Now we're increasing it because we're having too much negativity. That's where the hyper can come from. But of course, at some point, you gotta ask yourself, we don't want to stay hyper forever. We want to make sure we can get back to rest, because neurons want to go and be back at rest as well. So again, you will end up going back towards resting membrane potential, which is going to be polarized, and that is going to be -70 millivolts. So these terms are just going to happen over and over and over again as we go through the lecture, especially for the second part for Tuesday's lecture, because that's where we actually get to see and apply these numbers to action potentials, for example. Our terminology: polarized means your neurons at rest, -70 millivolts. Depolarized means that your membrane is becoming more positive, so it's going towards positive on your actual y-axis, and that means you are decreasing the membrane potential. Repolarized means that you're trying to return to rest, meaning you're trying to return to -70 millivolts. That's what repolarization is, and again, your membrane potential gets more negative. And then hyperpolarization means you go beyond the resting membrane potential. You get even more negative, so you increase the membrane potential to create hyperpolarization, until you finally go back to -70 millivolts, which is at rest. So now we have the terminology. Let's go ahead and get some general details to get your brain primed for Tuesday's lecture for graded and action potential. So we have our terminology. Let's go ahead and get some general info about our two signals when there is a change in membrane potential. That's what the most important thing is. So remember, change in membrane potential, you're going to get two signals: graded potentials or action potential. So graded potentials is what we're going to start off with first. Then we'll get into action potentials, and then we ask ourselves, well, how do we go between graded potential and action potential? That's what we'll use our little neuron here to help us with, okay? So first things first, what does that mean as far as change in membrane potential? That means there's a change of charge inside and outside the cell. So at rest, we know that the change in charge is -70 millivolts, but if you actually go outside of rest, we can depolarize and go up to maybe +30 millivolts, and then we can repolarize to go back to rest, and then hyperpolarize to go even further to -70, like maybe -90 millivolts, until we go back up to -70. Potentials, like it says here, is variable strength signals that occur when ion channels open and close in response to a stimulus. What does that mean? It means that we have our membrane, we have different leak channels. Those leak channels can be specific to potassium and sodium. And when some of those channels are open or closed in response to whatever stimulus the neuron is being given, that can create a graded potential. So let's go ahead and get an idea by just using our drawing down here. Now, graded potential is only going to happen in certain areas. It's only going to happen with the dendrites, as we see here, and the cell body. It's only going to happen when you have a stimulus or input from, to some kind of response in the cell itself. So that stimulus is going to go to our dendrites. Our dendrites are going to move that signal to the cell body. All right, folks? Now let's just get a little review here. I'm looking at an axon here. I have my axon terminals. I have my dendrites, my cell body. Right here, I'm going to have my good old trigger zone. It's also called the axon of Hillock. It's also called the initial segment. So just keep that in mind as we go along. So a greater potential is going to get a stimulus, and then it's going to then move that message through the cell body. And guess what? These particular messages can vary in strength. So sometimes you can have a stimulus that's very weak. And if you have a very weak stimulus, it still has the potential to travel down to the cell body. If you have a strong stimulus, it still has the potential to travel through the cell body. But if you have a weak stimulus or a weak input, you will get a weaker graded potential. And if you have a strong stimulus, of course, you're going to get a stronger graded potential. Okay, meaning it's probably going to travel further and it has the ability to hit that initial segment or trigger zone. So the type of signal for a graded potential is going to be an input signal. Location is always going to be dendrites and cell body of the neuron. It's going to travel in short distances. Why short distances? Because we're only traveling from the dendrites and the cell body or the soma. So that's not a large distance. The dendrites, even though it looks like they have all these branchings, they're actually quite short. So we got to keep that in mind as well. Now the question is, what is the type of signal? We have our little graph here. We know we're at negative 70. Let me make a better graph. We have our little graph here. Okay. And again, we know we're at negative 70. Of course, this is millivolts. And the type of signal that the graded potential can give is it can have a stimulus and say, hey, I'm going to give a signal to cause depolarization, which means it's starting at 70, it's polarized, it goes to depolarization at around plus 30, then it repolarizes, hyperpolarizes, and goes back to rest, right? That's a possibility. And then you have the situation where it can also hyperpolarize. So again, it can start at negative 70 and then hyperpolarize until it comes back to rest. Or sometimes it can hyperpolarize and then depolarize as well. We'll get into those details as we go along. So that's literally what you're looking at here. That's the whole purpose of that graded potential. Now the signal strength depends on the stimulus. If the stimulus is weak, weak graded potential. Stimulus is strong, strong graded potential. But there is no minimum level required to start a graded potential. So it doesn't matter. Once that dendrite gets that stimulus, it's moving to the cell body, period. It doesn't matter if it's strong or weak at this point. So that's going to give us some just general ideas of graded potentials until we get into that into the second part. Okay? Now let's focus on action potential. I'm going to erase all this because we will need more little graph areas. So action potential is all about having a signal, we're going to do all this, that's going to transport to the axon terminals and therefore be able to send messages, transmit through the axon terminals to send messages to other neurons, right? So what's going to happen is this trigger zone is going to be more important. Remember, it's called a trigger zone. It can also be called initial segment or axon of Hillock, okay? So just keep that in mind. Now, how do action potentials work? Well, first, you're going to have a stimulus come in that's going to go to the dendrites, to the cell body to create a graded potential. Now, if that graded potential is strong enough, and we're not saying it has to be weak or strong, but the graded potential has enough of a signal to be able to hit that trigger zone and cause the membrane to get a little bit more positive up to around negative 55 millivolts, then this will trigger an action potential. Okay, so just keep that in mind. Let's go ahead and write a graph. So we already know we're going to be at negative 70 at rest. And if that stimulus, let me just put a little dash line here, if that stimulus is large enough to just get our membrane potential a little bit more positive, around negative 55 millivolts, then an action potential will be triggered. And the beauty of action potentials are once they're triggered, it's going to completely happen. They're all or none. Okay, there is no like, oh, it's going to be triggered and maybe it'll happen. Once it gets to negative 55 millivolts and it gets triggered, then you're going to have a depolarization to around plus 30, and then you're going to go through the whole process of repolarization and hyperpolarization. Action potentials are output signals. Okay, they're going to be transmitting those electrical messages down the axon length into the axon terminal. The location is only the axon. They're not a part of the cell body. They're not a part of dendrites, only the axon. They can have the ability to travel long distances. Yes, some of them can be short, but also some of them can be long, like we talked about. If you want to make sure you're sending a message down to your knee, you need to make sure that you have long enough axons to do that. That means they can definitely travel those long distances. The type of signal is always going to be depolarizing. So yes, we saw that greater potentials can make the membrane change to be more positive or more negative, but action potentials will always make the membrane become more positive. Okay, go up to that plus 30 threshold. Okay, now what does that mean? That means when you're thinking of, well, wait a minute, if once we hit that threshold of negative 55, then how strong does it need to be able to complete that overall action potential? And guess what? All action potentials are going to be identical. All the signals for the action potential is going to be identical. So that means that that's going to have the same magnitude. So if you have a stimulus coming in, you can actually hit the negative 55 threshold, and then that's right, and you're hitting that negative 55 threshold at the trigger zone, then no matter how many of those same stimulus signals come in, all of the strength of those action potentials are going to be identical. That's what I mean by that. Now, of course, we said we initiate a threshold of approximately negative 55 millivolts. Okay, so again, threshold of negative 55 millivolts. And the beauty of action potentials is that they have that all or none phenomenon. So once the action potential hits that threshold and it starts, it transmits that signal. All right, let's go ahead and put this all together. And then we'll get into a worksheet question. We'll just do one. Let's go ahead and put this all together. So first things first, the neuron is going to receive the signal. The neuron gets the signal. Once it receives that signal, you get a graded potential. So here's that signal. It goes down and it creates a graded potential. We know this is our trigger zone. And this is the general aspects of it. Okay, we'll go into detail in part 2. Next, that signal is going to travel down the cell body, which I already showed you here, the graded potential traveling down the cell body. And if strong enough, what do we mean by strong enough? Negative 55 millivolts at that trigger zone, you will get an action potential. So let's say we hit the negative 55 millivolts, then we're going to have the action potential to transmit that signal. And that's it. Let's go ahead and get into one question on the worksheet, and then I'll see you for part 2. Folks, let's go ahead and do number 10. So which of the following statements about graded potentials is false? So that means we're looking for things that is completely wrong, and the things that are true we know is going to be not the answer, right? That's the approach for this question. So first it says graded potentials act as short distance signals. That is completely true. Why? Because we already know the dendrites are very small, and also the cell body is not as large in a lot of different ways. Okay? So yes, graded potentials act at a short distance. Because it's true, we know that's not the answer. Letter B. The magnitude of a graded potential is proportional to the magnitude of the stimulus. This is a lot of fancy words saying magnitude instead of the strength of the stimulus, for example. But yes, the magnitude, how large it is of a graded potential, is directly proportional to how large the stimulus is. That is definitely true. We said that if you had a strong stimulus, you're going to get a strong graded potential, weak stimulus, a weak graded potential. So we know since it's true, that's the wrong answer. Graded potentials occur mainly in the axon. We know that's false. Graded potentials are going to specifically be dendrites and cell body. So let's keep that in mind as well. Because this is false, we can automatically say that letter C is the correct answer. But we also need to read letter D just to make sure that we are verifying our work. Graded potentials can be depolarizing or hyperpolarizing. That's also true. We know that it can make the membrane more positive or more negative. So just keep this in mind as you're going along. Make sure you're looking from the lecture material and then breaking down the pieces as you're going along for each of these questions as well. Because sometimes, especially as we go forward into exam 2, which is going to be Canvas-based instead of Pearson-based, you will see that you will have to start breaking down some of the questions more and being able to glean information from those variables that you're trying to look for. All right, folks, I'll see you in part 2. Have a good one.